Every day, our planet is flooded with energy from the sun, our very own star. This energy travels 150 million kilometers through space to reach us, powering nearly everything on Earth. Without the sun, Earth would be a frozen, lifeless rock. The sun's energy drives our weather, warms the oceans, and fuels the winds and currents that shape our climate. Plants capture sunlight through photosynthesis, turning it into food that sustains almost all life, including us. When you eat, you're really consuming stored sunshine. The sun's output feels constant, but even small changes can have big effects. If the sun gets a bit brighter or dimmer, it can shift Earth's climate. That's why scientists measure the sun's energy with incredible precision. Knowing exactly how much energy Earth receives is critical for understanding our climate system. If we want to understand climate change, we have to start at the source, the sun. Measuring solar energy is the first step in building a complete picture of Earth's energy budget. This knowledge helps us predict and protect our planet's future. The sun's energy isn't just astronomy, it's about our survival. That's why we measure it, track it, and study it so closely. The story of how we do that is a story of science, technology, and our quest to understand our home. Let's see how we measure the sun's power. Scientists call the sun's total energy output total solar irradiance, or TSI. Imagine a 1 square meter solar panel in space facing the sun. TSI is the energy hitting that panel every second. Measuring TSI accurately is key to understanding Earth's energy input. Enter ACRIMSAT, a satellite built for one job: to measure TSI with extreme precision. ACRIMSAT stared at the sun day after day, creating a continuous, reliable record of its brightness. Why does this matter? Because the sun's output isn't perfectly constant, it varies in cycles. To spot these patterns, we need years of uninterrupted data. ACRIMSAT bridged gaps between older and future missions, ensuring we never lost track of the sun's behavior. Think of it as our planet's dedicated light bulb watcher, detecting even the tiniest fluctuations. These small changes can have big consequences for Earth's climate over time. ACRIMSAT's mission: turn theories about the Sun-Earth connection into solid facts. With precise TSI data, we can better understand how the sun shapes our world. That's the power of measuring the sun's total shine. How did ACRIMSAT measure the sun's energy? With the ingenious ACRIM III instrument. At its core, two identical ultra-black cones, one faces the sun, the other is shielded. The sun-facing cone heats up, the shielded one stays cool. The instrument uses a tiny heater to keep both cones at the same temperature. The amount of electricity needed to heat the shaded cone equals the solar energy hitting the first. By measuring this, scientists know exactly how much energy the sun delivers. It's a precise balancing act, like weighing sunlight with electricity. The instrument constantly calibrates itself, ensuring accuracy year after year. This self-checking design means reliable, long-term data. That's how ACRIMSAT built a trustworthy record of the sun's behavior. Smart engineering, simple principle, powerful results. The sun's energy changes are tiny, about 0.1% over its 11-year cycle. But even a small shift in such a massive energy flow can impact Earth's climate. Think of Earth's climate as a sensitive machine. A slight tweak in power input can warm or cool the whole system. Natural solar variations drive climate patterns and events like the Little Ice Age, linked to a dimmer sun. To understand human-caused climate change, we first need to know the sun's natural cycles. ACRIMSAT's precise TSI data lets scientists plug real numbers into climate models. This helps separate natural solar effects from those caused by humans. Without accurate solar data, we'd be guessing about what's driving climate shifts. ACRIMSAT gave us the numbers we need to understand our climate's past, present, and future. It's the foundation for reliable climate science. That's why measuring the sun matters so much. ACRIMSAT was part of a legacy, the ACRIM family of solar missions. It started with ACRIM I in 1980, which gave us the first continuous, high-precision TSI measurements from space. ACRIM II continued the record in 1991, flying on the Upper Atmosphere Research Satellite. Each mission handed off to the next, like runners in a relay, to keep the data unbroken. Gaps in the record would make it hard to spot real patterns or changes. ACRIMSAT, launched in 1999, ensured there was no gap after ACRIM II. This continuity is gold for climate science. Long, uninterrupted data sets reveal the most important trends. The ACRIM missions were a deliberate, decades-long effort to keep watch on our star. ACRIMSAT wasn't just a solo act, it was a vital link in a scientific chain. Its success ensured the priceless record of the sun's energy stayed intact. That's the power of teamwork in science. ACRIMSAT was different, a small focused satellite with one job measure TSI. Unlike big, multi-purpose satellites, ACRIMSAT was lean and efficient. Weighing just 113 kilograms, it launched on a Pegasus rocket and orbited in a sun-synchronous path for optimal solar viewing. Its design minimized exposure to Earth's shadow and radiation, protecting its sensitive instrument. Unlike earlier ACRIM instruments, which were passengers on larger satellites, ACRIMSAT was its own boss. This independence meant uninterrupted, optimized solar measurements. The single-purpose approach made the mission resilient and cost-effective. Sometimes, solving big problems takes a small, smart solution. ACRIMSAT's elegant design was perfect for its vital mission. It proved that focus and simplicity can deliver world-class science. ACRIMSAT launched in 1999 with a 5-year mission goal, but it far outlasted expectations, working for over 14 years. The satellite orbited Earth more than 73,000 times, delivering stable, high-quality data year after year. Its robust engineering and self-calibrating instrument kept the data trustworthy from start to finish. This long, consistent record was a huge bonus for scientists, eliminating the need to stitch together data from different instruments. In 2014, the mission ended as the spacecraft's batteries wore out. But ACRIMSAT's legacy was secure. It showed that a small, focused satellite could deliver big science. Sometimes persistence and smart design beat size and complexity. The little satellite that could truly deliver. Its data continues to shape our understanding of the sun and climate. That's a mission well done. ACRIMSAT's data transformed science. It nailed down the sun's 11-year cycle and showed how solar brightness changes with sunspots. This record is now a foundation for modern climate models. By combining ACRIM III data with earlier missions, scientists built a multi-decade dataset to spot long-term solar trends. The result: recent solar changes aren't big enough to explain rapid modern warming, clarifying the role of human activity. ACRIMSAT also became a gold standard for calibrating other satellites, improving Earth science across the board. Its precise measurements replaced guesswork with hard data. With the sun's input known, scientists can focus on other climate variables. ACRIMSAT didn't answer every question, but it made the climate picture much clearer. That's the impact of great data. ACRIMSAT's mission ended in 2014, but solar monitoring continues. Newer instruments like NASA's TSIS-1 on the International Space Station now carry the torch. TSIS-1 measures both total and spectral solar irradiance, giving even more detailed insights. This ongoing record is crucial. Science builds on what came before. The sun is the main driver of Earth's climate, so tracking its energy is essential. The continuous data record, built by missions like ACRIMSAT, is our guidebook to understanding climate change. Next time you feel the sun's warmth, remember the silent satellites watching over us. Their data helps us protect our planet's future. Curiosity, precision, and persistence. These are the keys to good science. Thanks to ACRIMSAT and its successors, we're better stewards of our amazing world.